Okay, in this video we're going to talk about the three views of complex multiplication. So the complex numbers, obviously we've been representing it as a plane. It looks an awful lot like the traditional plane R2. And I even note that addition works in exactly the same way. The vector addition here matches up perfectly with what it means to add complex numbers. You just do it component-wise in the case of R2, and you just do it real for real and imaginary part for imaginary part in the case of the complex numbers. It all looks exactly the same. So you might wonder, well, what actually is the difference between C and R squared? Why do we bother even talking about these two different objects and giving them two different names? And the important thing that separates C from R squared, that makes it strictly richer than R squared, is the fact that you can multiply elements of the complex numbers. It's something we've seen before, and it's something I'm going to explore in a few different ways in this video. And when I say multiply elements, you might complain, well, we can multiply vectors here. We have inner products, we have cross products, but those are boring for a variety of reasons. They're not completely boring, but they're certainly not as rich and interesting as the case of the complex numbers. Actually, they are related to the complex multiplication, but that's a subject for another video. So the first view is the first view that we ever saw. The flat-out multiplication the way you would think it should work. So I've just written it here just to make it nice and pretty with different colors so you can see these different things. A plus bi times c plus di. You can multiply a times c, you get ac. You get the a times di, you get ADI, etc. So I just FOILed it out, and you can verify that you get each of these terms, BDI squared and so on. Remember that the I squared is always equal to -1. So that becomes minus BD over here, and I've just lumped together the real parts and the imaginary parts here. Written this as U and this as V. And we get that's equal to U plus IV. So you should have remembered that from the previous video when I showed that the product of two complex numbers, numbers of the form A plus BI, a real number plus another real number times I, will always give you something of exactly this form. So you can always simplify it to this form. And one thing to notice is that if you actually take U squared plus V squared, right, that's the square of the norm of this complex number. So our complex number is U plus IV. That means that on the real axis here, the x-axis is the real axis, there's U, and the height would be on the y-axis, which is the imaginary axis. That's our V. And so the sum of the squares of these two legs of the right triangle is, as always, the length of the hypotenuse squared. So U squared plus V squared is the modulus, or length, squared. Modulus is a word that, for whatever reason, they like to use in the case of the complex numbers. So it's the modulus squared. And it's equal to, so we're just looking at the definition of U and the definition of V here. U squared is U times U, AC minus BD times itself. V squared is AD plus BC times itself. We multiply that, we add them up. So I just, expand it a little. You have AC times AC gives you AC squared. The negative BD, negative BT gives you plus BD squared. And you have two of these minus BD times positive AC terms, which will give you minus 2 ACBD. So I won't muck this up any further, but you can look at this, stare at it, and verify that eventually what will happen is that these cross terms, negative 2 ACBD, will cancel with these cross terms, and you'll end up with just AC squared plus BD squared plus AD squared plus BC squared. So let me write that out actually. That's AC quantity squared. And AC squared is the same. You can distribute the square, and that's just A squared C squared. So I'm writing here something in red. Let me be very clear about what I'm doing. I notice that these two kind of cross terms that don't involve squaring anything cancel. ACBD is the same as ADBC. The order doesn't matter. So those I'm going to cancel. And I'm just focusing on these four remaining terms that involve something squared, but I'm going to distribute that square. That's all I'm doing here. A squared C squared plus B squared D squared plus A squared D squared. I'm on that one now. Plus, and then finally B squared C squared. And then you can just notice that, hey, you can factor this out, and it becomes a squared plus b squared times c squared plus d squared. And why is that interesting? Well, because if you go back to these original numbers that we started off multiplying, it was a plus bi. The modulus squared of this would have been the real part squared plus the imaginary part squared, for the same reason as this picture. And the same thing with c squared plus d squared, the other complex number. Its modulus squared, its size or norm squared or length squared, would equal c squared plus d squared. So what we just found is that the length of the product of the numbers, which is u squared plus v squared, or the square root of it, is actually equal to the product of the lengths of the original numbers. So there's this nice interesting property. The modulus of, say, z times w, if z and w are complex numbers, is equal to the modulus of z times the modulus of w. And that's something you can read from the algebra using this kind of basic, naive version of complex multiplication. Here's a second view that'll show us that not only can we figure out the length of the product after we know the lengths of the original numbers, we can actually also figure out the argument, the angle of the product right there. We can figure that out too. But this time we can look at these complex numbers in polar coordinates, right? So remember that originally we talked about polar coordinates. It shows you what the length is explicitly. You write these numbers as re to the I theta, where r is the modulus, or the length, and the theta is the angle, the argument. And of course we always take the angle to be the angle from the positive real axis, or the positive x-axis. And that's the angle there. And if you don't remember why we're expressing it with this weird exponential notation, you should go back and watch the video on Euler's formula. So we have the length times e to the power, which is I times this weird imaginary power, I times the angle. Alright, so if we have two complex numbers here in blue and in green, re to the I theta and rho e to the I alpha, let's say, then, well, if you just again kind of use the obvious properties of algebra here, we can move these two real numbers. Again, r, theta, rho, alpha, these are all real numbers. R times rho out front, and we will call that capital R, and then e to the I theta. I mean, listen, e to the I theta times e to the I alpha is the same as, well, when you multiply exponentials, you're just adding the exponents. E to the I theta plus I alpha. And then you can just factor out an I, and that's how I get this term here. E to the I theta plus alpha. And that theta plus alpha, the sum of those angles, I'm just going to call it phi. So I can rewrite this as capital R times e to the I phi. Okay, so that's another way, by the way, of showing that the product of two complex numbers is, again, a complex number that's closed under multiplication. If you're thinking of it in polar coordinates as opposed to this kind of Cartesian real and imaginary component version of it, then it still looks the same. So what we've realized, or what we've seen, is that capital R is equal to little r times rho. I mean, anytime you have a complex number written in this polar form, that real number out front is always going to be the length. It's always going to be the length. And that little number up there, e to the I times something, is always going to be the angle. Okay, so what we've just seen is that the length of the product is equal to the product of the original lengths. And also the fact that this angle here is the sum of these angles, we see that the angles add. So the lengths multiply. We see that again this way. This time we see something even stronger. We see that the angles add. You might wonder, could we have seen that the angles add just by using this first view, this arithmetic property here? And the answer is yes. I mean, what you would have had to do is look at the quotients of u and v. How do you determine the angle? Well, one way of determining the angle is to simply say, look, I'm going to think of my vector. Let's say there's the angle theta. And let me just draw out the full right triangle. So there's your imaginary part. There's your real part. And you can say, well, the tangent of this angle is the imaginary over the real, right? Just opposite over adjacent. So you can take the inverse tangent of the imaginary part over the real part, And if you want to compare that here for u and v, if you take v over u and compare it to b over a and d over c, then you will in fact see that they add. So it's a more ugly computation. I don't want to bother going into it. But yes, you could have used the first view to see that angles add to. But it's particularly nice in this polar view. Alright, so let's actually get an idea of what this actually looks like geometrically, right? The nice thing about these polar coordinates is that they bring the geometry of the complex numbers right out for you, right? The r is the length and theta is the angle. Alright, so I've drawn here two vectors here. I've shown what the r and theta is. So this is our r e to the I theta. This tip of this vector here is r e to the I theta. And the tip of this green vector here is rho e to the I alpha. And so what we're saying is that when we multiply these numbers, what we're doing is the length of the new number, let me move over to black here. The length of the new number is going to be the product of these lengths. So let's say rho is like less than 1, so that multiplying by rho shrinks r. So then what will happen is we'll end up with something maybe of length, oh, I don't know, if rho is about half of r would be around here or something like that. So let's say that's going to be roughly our length. But what's our angle? Our angle is the sum of these angles. It's this theta plus the full alpha. So you take this theta, this little chunk I've drawn right here, and you add it to this alpha, and maybe it comes out to just a little bit right there. Alright, so now we know the length of it is the product of these lengths, and we now know the angle is about right there. So let's see if I can draw this, and hopefully this makes sense. That length should be r times rho. Again, I assumed rho was less than 1, so it actually shrinks things. And that's e to the I, and I just added the angles, theta plus alpha in there. Let's see it. Alright, so hopefully that gives you some idea about it. But what's nice is to think about it, I think a nice way of thinking about it is to say, well, what happens if we just multiply it by r? Remember, r is just a real number, it's just a length, but if theta is equal to 0, well, first of all, from a purely algebraic standpoint, e to the I times 0 is just e to the 0, which is equal to just 1. So multiplying by e to the I theta doesn't matter when theta is 0. So we can think of r as the same as r e to the I times 0. Sorry, not theta. Not theta, 0. Okay, so we can think of r in this way, just because e to the I0 is 1. Okay, but 0 means we have an angle of 0, which would put us right here. So let me actually just quickly draw what I'm talking about. So if r is a real number, we can think of it as lying on this axis because it has angle 0. And that should make perfect sense, right? Say there's r, just length r right there. That should make perfect sense. Everything works out perfectly because traditionally we do think of that as the real axis and that as the imaginary axis. So it makes good sense that when you have an angle of 0, that is to say when you actually are a real number, you should lie on the real axis. So it all works out nicely in that way. So what happens if we multiply by just r? We can think of it in this way. So you're multiplying by r. For example, it's the same rho e to the I alpha. It would be r times rho e to the I alpha. And there's no angle. The angle's 0, so the angle adds nothing. So that's it. All that happens is, if we call that r e to the I phi, well, the phi is still equal to alpha because we didn't change anything. So the angle stayed the same. Except now, this capital R is equal to r times rho. Right? What happened is the lengths multiplied, but the angle stayed the same. See, that's what happens when you take an arbitrary complex number, like rho e to the I alpha, and you multiply it by a real number, r, that doesn't have any argument, that doesn't have any angle component to it. It just affects the length without affecting the angle, which makes reasonable sense, right? In scalar multiplication, thinking of these things as vectors, elements of R2, multiplying by a real number would scale it. Well, that's the same thing that happens here. So hopefully that answers the question, what if we multiply by just r? Well, here's a more interesting question. What if we just multiply by e to the I theta? That is to say, what if r is equal to 1, right? Because if r was equal to 1, then 1 times e to the I theta, well, there's no need for me to keep writing this 1 here if you're multiplying. That's the same as e to the I theta. So really what I'm asking is, what happens when you scale and rotate, except for when you scale by the number 1? Well, of course, multiplying by 1 doesn't change anything. You still have r equals little r times rho, but little r is now 1, so that's just rho. So it's the length that stays the same this time around, not the angle. The angle does change. You're still adding that theta. So e to the I theta times rho e to the I alpha is equal to, well, it's still the same rho, the same length, but now it's e to the I theta plus alpha. So I guess what I'm trying to say is that, you know, the length components, these real numbers out front, really tell you everything you need to know about scaling and how multiplying by this number is going to scale things. And these angle components, these things up in the exponent here, these thetas, alphas, phis, they tell you all about the angle, and they only affect the angle. So you have these things really separate. I mean, it's not like you have to know what the length of the complex number is in order to know how much it's going to be rotated. You only need to know the angle, and vice versa. If you want to know how long it's going to get stretched or scaled, you don't need to know anything about the angle. You just need to know what that number out front is. That's what I'm trying to communicate here. So, but this is an important point. So, when you're multiplying by e to the I theta, this is so important, it's worth actually writing out. Multiplying by e to the I theta has the effect of rotating by an angle of theta. And of course, this is in the counterclockwise direction. Okay, so rotating what? Well, rotating the number that you're multiplying it by, right? You pick a number, z. If you want to multiply it by e to the I theta, all you're going to do is you're going to take, visually, you're going to take z as a vector, and you're just going to rotate it by theta in a counterclockwise direction. So now we've seen two views. The first view is nice because it's very algebraic. It's kind of basic. It's the way we've defined things in the first place. The second view is even nicer, in my opinion, because it really brings out the geometry of everything that's going on. It shows you how the lengths multiply, the angles add, and that's something you really want to keep in mind with complex multiplication. The geometry of it. Lengths multiply, angles add. Multiplying by just a real number scales it, and multiplying by just something of the form e to the I theta rotates it. And doing both will rotate and scale. So multiplication by complex numbers collectively, in general, consists of a rotation and a scaling. Rotations come from these guys, scalings come from those guys. But, I mean, rotation and scaling in the plane, that's something you've probably seen before if you've taken a course in linear algebra. So the third view is I'm going to take a look at how this all works from the perspective of linear algebra. So let me be very clear about exactly what I'm going to be doing here. If we think about it, if z is, I don't like that, if r e to the I theta is a very specific complex number, okay, so this is fixed in our conversation right now, then you can define a function that takes the complex plane to itself, that takes in a complex number, spits out a complex number. And how is it defined? If you feed in the number z as a complex number, then it just takes z and it multiplies it by this fixed number, r e to the I theta. Okay, so this is like if this were reals instead of complex numbers, this would just be y equals mx, basically. You're just multiplying by a number. That's all we're doing. Except here, we're multiplying by a complex number. Okay? So this defines a mapping of the complex numbers to the complex numbers. And what does it look like? Well, we just spent a whole lot of time talking about the fact that this looks like a scaling plus a rotation. Stretching and rotating. Okay, well, if we forget for a second, remember at the very beginning of the video I said, what's the difference between complex numbers and R2? Just the complex multiplication. If we forget about that, geometrically, we can think of this as R2. So if we want to think of that same exact function as a mapping of R2 to R2, well, we can ask ourselves an interesting question. We can say, hey, you know, back in linear algebra class, we would look at such mappings, but we wouldn't just look at any such mappings. We'd be particularly interested in those mappings which were linear. That was an extra condition that you could put on a mapping. Any map that takes, points of the plane and spits out points of the plane, that's boring. I mean, it's hard to say anything interesting about it. But if it respects the vector space structures, that's interesting. And those are things we can model with matrices, and we can say all sorts of great things about it. And, I'll leave that to a course in linear algebra. But right now, you can think of this function f as a mapping from R2 to R2. These are both vector spaces, and you might wonder, for this particular mapping that I've drawn here, just this kind of scaling and rotating, multiplication by a fixed complex number, is that linear or not? And if you're familiar with linear algebra and you remember linear algebra, then of course you'll probably say, well, yes, it is, because scaling is something we know how to do with matrices, and so is rotation. So that's what the third view is going to be. I'm going to take a look at it from a more linear algebraic perspective. So in linear algebra, remember that 2D rotations, and again, we're rotating by an angle of theta in the counterclockwise direction, they all look like this 2 by 2 matrix with the cosines in the diagonal and sine and negative sign in the off diagonal. And scalings look like R0, 0, R. If you don't remember that, well, you're not convinced of that, what does a scaling look like? If you have a vector uv and you want to scale it, you want to stretch it by a factor of r, you would just multiply it by r, right? So that it would be r times u and r times v. You'd separately scale the x and y components. Okay? But I claim that that's the same as r times the identity matrix. So the identity matrix doesn't do anything, right? It's like multiplying by 1. You can always plug it in wherever you want to plug it in. Times uv, right? If you ignore the r for a second and you just focus on this product, well, you're just going to get uv. So it's the same as that. But now you can say, well, r times the identity matrix, again, scalar multiplication to a matrix just hits every single component by that scalar. That's going to just look like r0, 0, r times uv. So that's my little explanation for why scalings are given by matrices that look like that. Okay. Or, other ways you could have said it. You can actually just explicitly multiply this by uv, and what do you get? Row by column pairwise multiplication. Your first thing is ru, and then the next row times that column is 0 times u plus r times v. That's rv, which is exactly what we got here. So I'm just beating a dead horse. But the point is, this is what, switch back to red here. This is what rotations look like, and this is what scalings look like. So if you want to do a scaling and a rotation, which is the kind of thing we were talking about here, right? We have scalings and rotations. Then it's given by just a product of these two matrices. And just for kicks, let's actually write out what this looks like. Alright, so row by column pairwise. There's our first row, there's our first column. R times cos theta. Okay, first row, second column is going to be negative r sine theta. Next row, second row, first column is 0 times cos theta plus r times sine theta. And finally, it's going to be another r times cos theta in the bottom right. So just for kicks, that's what it looks like, as you would expect. Combining gives this. Okay, but r e to the I theta, again, the r part scales, the e to the I theta part rotates, is the same as r times cos theta plus r sine theta I. So remember, this part was the bit of the Euler's formula. Here we're using Euler's formula. That's how I originally motivated that you could write down complex numbers with this weird e to the I theta notation. Right? R cos theta makes sense, just to remind you. Right? How would you do it? If you were trying to find x and y coordinates of this vector, you knew what the angle theta was and you knew what the length r was. Well, r cos theta just by trigonometry would give you this x coordinate. And r sine theta, again by trigonometry, would just give you, just by definition of cosine and sine, would give you the y component there. So it makes sense to write it like this. And then when I showed that cos plus I sine theta, so I'm just reminding you what we did in Euler's formula video. I showed you cos times sine theta plus I was equal to e to the I theta, Euler's formula. I was a little fishy about how these things get defined, but hopefully I convinced you. And r cos theta was the x coordinate, so I'll call that a, the real part, and r sine theta was the imaginary part. I'll call that b, the y coordinate there. So a plus bi, right? Okay, so if you actually plug a plus bi into this matrix, I mean, what do you get? Here we have an r cos theta, right? So this matrix, remember, just came from what happens if I scale and I rotate. I just multiplied the two matrices. Doing one then the other just consists of multiplying the matrices, right? From linear algebra. But r cos theta is equal to a. It's the real part, right? So that's the real part of the complex number. And this negative r sine theta, well, r sine theta is b. That's the imaginary part, so that's negative b. So then if we fill out the rest of it, r sine theta is b and r cos theta is a, you get this interesting matrix built up out of the real and imaginary components of your complex number. So hopefully I'm creating this mysterious connection in your mind between the complex number a plus ib, or a plus bi, and this matrix a negative b, ba. This mysterious connection is going to come up again and again. I'm going to highlight how we can kind of use what we know about linear algebra from this perspective, and even advanced calculus, which remember is an extension of linear algebra, to the nonlinear setting. This is going to give us an interesting perspective on what it means to multiply by complex numbers, and it's really going to allow me to explain even better why the complex numbers are so different than the real numbers. It has to do with complex multiplication. Real multiplication isn't so fancy, but complex multiplication, I mean, it's not just any old linear transformation. It's a linear transformation of a very specific form, and that's something we're going to see. So finally, just to show you, how these things kind of work out and verify that it all makes sense to think of these numbers as these matrices, let's just see what will happen here. If I have a plus bi and c plus di, we can think of them as these corresponding matrices, where you put real component, negative imaginary, imaginary real, and so on. And if we actually multiply these things out, row by column, this times this, it would be a times c plus negative b times d. It would be ac minus bd. And then a negative b times now the second column, so first row, second column, would be negative ad minus bc. And then second row, first column, would be bc plus ad. And then last row versus last column would be negative bd plus ac. So again, notice that indeed it's of the same form. This looks the same as that, and this looks like negative that. But let's look at the first view again. Just what did we get in the case of the first view? When we multiplied it out, let's actually zoom back up and see what we got. Right, we got AC minus BD and AD plus BC. So we got AC minus BD plus AD plus BCI. And if you actually pay attention to it, what's going on is, thinking of this new complex number, that was what I called the U and that's what I called the V before, thinking of this new complex number as a matrix, U negative V VU, would give you precisely that matrix. So this connection is actually a rather strong connection. What I've shown you so far is that even if you're thinking of these things as matrices and you want to multiply them, that thinking of them as matrices and then multiplying as you would matrices gives you the same result as if you multiply traditionally as complex numbers and then you think of it as a matrix. So it all kind of fits together. So hopefully this connection is seeming stronger and stronger, but it should still be pretty mysterious so far. And I hope you guys still remember linear algebra. It would be very mysterious if you forgot some linear algebra. But anyway, let me give you a specific example of a very specific and interesting number. The number I itself, right? You can think of it as 0 plus just 1 times I. So its real component is 0. Well, that makes sense. It's an imaginary number. You would expect its real 0. And its imaginary component is just 1, right? It's the coefficient of I. As a matrix, this would correspond to, well, the real component is 0, so the two diagonals are 0, and the off diagonals would be negative 1 and 1. Okay? If you actually draw what I looks like, well, first of all, we already know what it looks like. This is the imaginary axis, so I is just a unit length vector pointing up at 90 degrees. It's on the y-axis, of course. Its length is 1. You can prove that just by saying, well, what's 0 squared plus 1 squared? It's real component squared plus its imaginary. It's x coordinate squared plus y coordinate squared. And 0 squared plus 1 squared is 1. Square root of 1 is 1. So it equals 1, as you would expect. And if you don't believe me that its angle is 90 degrees, I mean, obviously it should lie on the imaginary axis, but if you're really angry about it, well, you can think of 1 times e to the I pi halves. And what is that? Well, it's just, again, by Euler's formula, 1 times cos pi halves plus 1 times sine pi halves times I. But what is cosine of pi halves? Remember your little circle, your trigonometry circle here. The x-coordinate is always the cosine, and the y-coordinate is always sine. So pi halves would put us at the top of the circle, which has an x-coordinate of 0, so that's 0, and a y-coordinate of 1. So that'd be 0 plus 1i, which is just I. So indeed, 1 times e to the I pi halves is indeed equal to I. It has unit length, it has angle pi halves. Now geometrically, what does this correspond to? Multiplying by I scales by this. Right? Remember, that thing out front, that real number out front, is the scaling factor. So it scales by 1. But scaling by 1 doesn't change the length. Multiplying the length by 1 leaves it the same. And it adds this angle. Remember, angles add. It rotates it by an angle of pi halves. So it rotates by pi halves, or by 90 degrees in the counterclockwise direction. So that's geometrically what multiplying by I should do based on the conversation we started with before I mentioned all this linear algebra stuff. But if you want to test your linear algebra again, then think about what this matrix actually corresponds to. 0, -1, 1, 0. When you multiply it by something of the form xy, it'll give you -yx. Verify that, this times this and so on. -yx. And the slope of -yx is equal to, well, the change in y over the change in x. And when you compare that to the original slope, which was the change in y here would be the x. And the change in x would now be -y. And if you compare that to the original slope, which was y over x, the change in y over the change in x, then you've taken the reciprocal and you've multiplied by a negative sign. And maybe there's some small part of your brain that remembers from basic algebra class that that's how you flip it and flip by 90 degrees. Do a 90-degree rotation. So it all works out geometrically. So we have 3 views. You can think of it in terms of these matrices, which we're going to see again and again. And you can think of it geometrically, scaling and rotating. And it works out nicely with this modulus and argument formula. And of course, there's the traditional view.